I'm continuing on then with the discussion of the Pythagoreans and their philosophy. And today I want to talk about perhaps their greatest discovery, and I think perhaps also maybe the greatest discovery of all of philosophy in the ancient world. It had reverberations that are still with us today. It was a monumental discovery. And today I want to take you through it so that by the end of this lecture you'll understand exactly what that is. But first let's recap on the Pythagoreans, or the Pythagorean discoveries that we have before us so far, what we've already discussed. We have two things. The first is the discovery of harmony. This was an important discovery, an important relationship between music for them and for their discoveries in mathematics, a relationship between fractions that are contained in the tetractys, and musical harmonies. This was a significant enough discovery, and it was obviously made fairly early on. The second was a slightly more dubious discovery. It was really a sort of the attribution of numbers to significant things, to make those things into, to give those things the significance that the numbers might have had, or to lend significance to the numbers. You can read it either way. This was carried very far in the ancient world. It was a form of numerology, or it turned into a form of numerology. And say 500 years after the Pythagoreans, this numerology was all over the ancient world. And it was of arguably detrimental to the thinking, the clear thinking of many of the ancients. But let's leave that to one side. What I want to do today is to talk about the more significant of the discoveries. First of all, I want to say also that I said earlier on that the Pythagoreans wrote nothing down. Well, that's true in the life of Pythagoras himself. From the beginning, remember Pythagoras was born at the beginning of the 6th century BC, 6th century BC, and died probably maybe the early years of the 5th century BC. Now, during that time, the Pythagoreans didn't write anything down. They were a fairly coherent group, and they existed, as I said before, in Croton in southern Italy. However, towards the end of the 6th century, the Pythagoreans were attacked physically, that is, militarily. And this disrupted their status in Croton as a leading force. It caused some to flee and to go to other cities. They were attacked again in the middle of the 5th century, roughly around 455, 445 BC. And that was a fairly devastating attack. There are a number of leading Pythagoreans gathered together in a house to discuss matters of state. And the house was attacked and burned, and many died. Several escaped, 2 escaped. One of those is said to be the Pythagorean Philolaus. Now, perhaps because at that point then the Pythagoreans dispersed even further, the previous vow of silence that had existed under Pythagoras was dissipated or lost. And so what one finds is that from that point onwards, there are various Pythagoreans who do write things down or were alleged to. One of those was Philolaus, born probably at the early years of the 5th century, maybe around 580 BC, and probably not in the time, that is after the time of Pythagoras himself, probably didn't overlap. But he seems to have been of an adult age, strong, capable, around the time of the second attack on the Pythagoreans. For whatever reason, he did write things down. The Pythagorean doctrines were written down by Philolaus, and so we do know, probably 100 years after the early flourishing of the Pythagoreans in Croton, we do have written attestation to what the Pythagorean doctrine was. And it's sufficiently close to the origin of the Pythagoreans that we can be reasonably sure that these established doctrines go back to the early part of the Pythagoreans themselves. Thus we know that the doctrine of harmony should go back to the 6th century. And what I'm going to discuss today, I'm going to argue, should also go back to the 6th century. Okay, so we start with a square where the sides of the square are 1 unit of length. We fix it at that, 1 unit of length. Now, if we consider the diagonal of that square, either of the 2 diagonals of that square, then we can work out, using the Pythagorean theorem, a squared plus b squared equals the hypotenuse squared, that 2 sides of 1 mean that the hypotenuse, the diagonal, has to be square root 2. 1 squared plus 1 squared equals the square of the hypotenuse. Therefore, if the square of the hypotenuse is 2, then the hypotenuse is length square root 2. Okay? Simple. Now, we're going to just chop off half of the square, and we're just going to consider a triangle, the right-angled triangle, of the sort of bottom half, as it were. Okay. So we've got a triangle, right-angled triangle, and we've got the hypotenuse. Now, the question is, what length is that hypotenuse? We've said it's square root 2, but what is square root 2? What number is that? Now, if we suppose that is some kind of fraction, obviously it has to be something between 1 and 2, bigger than 1. It has to be, we'll guess for the moment, smaller than 2. So what is it? It's in between 1 and 2. What is that thing? Suppose we imagine that it's a fraction. Call that fraction m over n. M over n, for some m and n, where m and n are ordinary numbers, m over n equals square root 2. Okay, that's our supposition. And we're going to further suppose that fraction m over n has been reduced as far as it can be. It's been cancelled as far as it can be. That's basic primary school maths. Okay, so it's in what it's called its lowest form. So m over n is a fraction in its lowest form, and it equals square root 2. Okay. Now, let's square both sides, and what we get is m over n all squared equals 2. Okay, now we can separate that out to m squared over n squared equals 2. Okay, m squared over n squared equals 2. Now, let's multiply both sides by n squared. We get m squared equals 2 times n squared. M squared equals 2 times n squared. And what can we infer from that? Well, n squared is a number, but any number multiplied by 2 has to be even. So what we know now is that m squared is an even number. Now, if a number squared is even, then the number has to be even, because you would have a number multiplied by itself giving you an even number. Well, those numbers can't be odd, because if they were odd, then it would be an odd square. If it's an even number, then the numbers themselves have to be even. So now we know that m is an even number. M is an even number. But now we can infer from that n itself has to be an odd number. Because if m were even and n were even, then they would be cancelable by 2. But we've already said that the fraction is in its lowest form. It can't be cancelled any further. So if m is even, n must be odd. Okay, now let's take, if m is even, we've now got that. Let's say that m is equal to 2 times a number. It's 2 times, because it's even, it's 2 times a particular number. Call that number a. So we've now got m equals 2a. Now we substitute that back into our original equation, and we now get that 2a all squared equals 2 times n squared. Now 2a all squared is 4 times a squared by itself. 4 times a squared equals 2n squared. But now we can cancel 2 on both sides, and we get 2a squared equals n squared. But now we can apply the same logic as before. If 2 times a squared equals n squared, then n squared has to be even, and that means that n must be even for the same argument as before, because only an even number squared would give you an even number. So n now has to be even. But we proved before that n has to be odd. So now we have that n has to be odd and n has to be even, and that's a contradiction. That's the contradiction. That's the absurdity. So we made a supposition right at the beginning that we have square root 2 equal to a fraction m over n, and that fraction is in its lowest, its reduced form. Now we have shown that that supposition leads to a contradiction, that n is both odd and even. That can't be. Therefore, now we know that our original supposition must be false. Our original supposition that there is a fraction, m over n, that corresponds to the square root 2, cannot be true. That supposition cannot be true as a matter of logic. The argument form here is called reductio absurdum. You assume something in an argument. It has to be a strictly deductive argument. You assume something in your argument, then you infer from that supposition what follows, and if at the end of that argument you reach a contradiction, then now you know that the original supposition has to be false because it led to a contradiction. That's the argument form of reductio ad absurdum. And it may be that that argument form was also originated in the Pythagoreans, because we don't know of any instances before this. Okay, so now we have an argument to an absurdity, to a contradiction. That means to a contradiction. Now we know that our supposition is false. So we know that there is no such fraction that equals square root 2 as m over n. There can't be one. So what is square root 2? It's not a whole number. It's greater than 1, less than 2. It's not a whole number. It's not a fraction. So what is it? What is square root 2? If you just think about this for a second, you'll realize that this is a monumental discovery. Effectively, what the Pythagoreans had discovered is that there were numbers that go beyond the numbers that were known. The numbers that were known were just the counting numbers, 1, 2, 3, 4, 5, and the fractions. That was all that was known before this. And suddenly, here was an argument, a watertight argument, that shows that there have to be numbers that go beyond those numbers. And they're numbers that you can't easily say, it turns out, what those numbers are. You can point to them, you can say square root 2. What more can you say? Well, it turns out you can say more. But anyway, what I want to say is, to be clear, the Pythagoreans didn't themselves conclude that. They didn't conclude this statement about numbers in a very direct way. Plato, in his time, seems to have come to that conclusion, that there were these numbers that went beyond our ordinary numbers. But the Pythagoreans thought of these things in geometrical terms. And so what they thought about this was that there were lengths that were incommensurable with one another. Set a ruler however you like to measure a side accurately, so that it measures the sides of a square accurately, measures the sides of a right-angled triangle accurately. And the hypotenuse, the diagonal, cannot then be measured accurately by that ruler. No ruler can do that. No ruler can have exact markings which will measure the sides and at the same time be able to measure the hypotenuse. None, not a single ruler in existence could do that. And they took it that, the Pythagoreans took it that, well, what this means is that we have two things in the world, two lengths. We have which are not measurable together, which are not co-measurable. They are incommensurable, can't be measured by the same measure, by the same ruler. So they are incommensurable. And these two lengths, well, they are what? How does that come about? How do you have lengths that are not able to be measured together in this way? It struck them as a peculiarity, a strange thing about geometry, because the Pythagoreans really did think in terms of geometry, not so much in terms of numbers themselves. Numbers were only really a gateway to geometry. So they were interested in numbers, certainly, no question about that. But the fundamental reality was geometry, geometrical entities, things that were shapes in space. What had they now discovered? They had discovered that there were these lengths of ordinary entities, had to be in some sense definite, but were not commensurable with one another. For example, we just look at the right angle triangle again. Well, you've got the sides. They're a definite length. They're length 1. Set that. We've now got the hypotenuse. It's a definite length. It goes from one corner to another. It's not somehow more or less or deficient. It's a length. And yet, that length cannot be a fraction. It cannot be a fraction. Suppose we were to switch it around. Suppose we had set the hypotenuse at length 1, which we could have done. What would then happen to the sides? Well, if you want to work this out, you can find out that the sides, the two sides of the same length, are now 1 over square root 2. 1 over square root 2. Now, that's a fraction, but it's not a fraction of the form m over n, because the denominator is this strange thing, square root 2. So it's a very unusual thing. So in other words, you can assign one, we've got a side length and we've got a hypotenuse, a diagonal. We can assign one of them a unit length, or a measurable, a length that is measurable by our given ruler to equal some particular fraction. Whatever we do, however, that will mean that the hypotenuse is not measurable by that ruler. What does that mean? It means that suppose we had any ruler, no matter how fine the markings on that ruler were, no matter how fine, imagine them as fine as you like. Imagine them fine as you like, marked out on a ruler. If you put that ruler, if it measures the side as a fraction, if you put it against that hypotenuse, that will be a length that falls between two of the markings on that ruler. It will be between two of the markings on that ruler, no matter how fine the markings are on that ruler. Now do you see? This is astonishing, staggering. Now, in the Pythagorean period, in the 5th century, it's probable that the only number that they could see this in, and the only number for which they had a proof early on, was square root 2. In the Platonic period, in the 4th century, you get significant advances on this. And so more and more numbers were found to be such that their square roots were of this same kind as square root 2. What do they called rational numbers? Rational means, in some ways it means a ratio, yes, but it also means that you can say what that fraction is. You can say exactly what it is. Exactly what it is one number, an ordinary number, over another ordinary number. That's what a fraction is. What then were, if those things are sayable, what then do you say about square root 2? What did the Pythagoreans say about this? They said that they are architos, that they are unsayable. Here are numbers that are unsayable because they can't be said in any way other than to say, to point to them via a description. Oh, it's whatever a square root 2 is. That's the description. But they can't say in any more detail than that what that number is. So they are unsayable. And that means they are irrational. They are irrational numbers. They are not ratios. They are irrational. And irrational seems to also have this other meaning of unsayable. Irrational, unsayable. Not accessible to reason. Well, that's not entirely true. Reason can say more about this than we've already said, but it cannot say what that number is in a numerical form. It can just simply point to it as square root 2. Now, you could have learned this in school, by the way. Go through the argument that I gave you, which, by the way, is probably the argument that Pythagoras or the Pythagoreans themselves early on had. Go through that argument. Every step of that argument is accessible to a primary school education. Primary school maths should have been able to have told you this, and perhaps at some point in your education, grade school, primary school, whatever you want to call it, you could have encountered this, but my guess is that you would never have had this explained to you in any way that would make it stand out as important. And yet, for the Greeks, it was of resounding importance. As I say, as you move on from the 5th century to the 4th century, you come then to the gradual realization in Plato, in the last of the Platonic dialogues, that maybe what we have here is a whole new set of numbers that we didn't know about before. A whole new set of numbers. How many numbers do we have in this newly discovered set of numbers? Well, it turns out, and this is the next shock, that the number of these newly discovered numbers, the quantity of them, if you like, how many of them are there? They vastly outnumber the fractions and the whole numbers. There are many, many more of them than there are fractions. And that is provable. It wasn't proven until much later, but probably guessed much earlier, and guessed perhaps even as early as the late Platonic period. But at any rate, Plato was the one willing to take that step. Here we have numbers, not just strange geometry, but numbers that go beyond what we have already, in our sort of ordinary way of looking at the world, already hypothesized about, or fractions and whole numbers. Here we have something more. And that more points to something deeply, deeply interesting and unseen to that point about the universe. There have to be these numbers. Plato took that step probably, certainly in the later period, as you go into what's called the Neoplatonic period, say 4th, 5th century AD. Then we have the growing recognition of these things. And it led to, well, many things. It led to, for one thing, a deep understanding of what geometry was really about. Partly this flourishing was vastly facilitated by Euclid, who existed probably not long after, probably existed at the same time as Plato, but the Euclidean Elements, the book, was probably written just after Plato's death. But anyway, Plato may well have been, as it were, known about this. He doesn't mention it, but he may well have known about it. But what we have in Euclid is a vast elaboration on this topic, so that this idea of incommensurability is given more and more space and developed further and further. We know that existed, that some of that was done earlier in Plato's own lifetime, because he mentions the mathematician Theaetetus, and even goes into a digression in the dialogue with Theaetetus, goes into a digression on what the mathematician Theaetetus has discovered about these incommensurable magnitudes. He had discovered that, for example, the square root of 3 also is an irrational number, or gives you an incommensurable magnitude, that 5, square root of that, is also, etc., etc. In fact, any number, it turns out, any number that is not a perfect square has a square root that gives you one of these irrational magnitudes, these irrational numbers. They knew it up to 17, and they hadn't gone beyond that in Theaetetus. Later, they did go beyond it, far beyond it. That theme is what I'll take up next time. Further development with an extra proof, simpler proof, on irrationality of square root 2 and the implications of all of this. I'll see you then.